we've been talking about logistic regression so far, and so now that we understand how the model is built, we're going to first specify some priors, investigate the implications of those priors, and then proceed to fit the model. These are the next steps that we have to take. Just to remind you what the data set looks like, this is the recall data. We have for multiple subjects, we have for different set sizes, we have correct or incorrect responses in the experiment that they did, in which they had to recall a word in a particular row of words, right? So the answer that they are going to give is either correct or incorrect, and so what we did is that for the different set sizes, first we centered the set size, as I explained earlier, and we're going to use that centered set size as our predictor. So these values, the centered values, can be negative or positive, and they're the mean of this vector of centered set size will be 0, and that represents the mean set size. Okay. All right, so what does the model look like? We are going to model the probabilities in the Bernoulli likelihood, right? And we are not fitting the model to 0-1 responses, even though the software that you use may actually do that, right? But internally, the model is doing something different, right? And so what we are going to do is we are going to model the effect of set size on the log odds rather than on probability, okay? All right, so how do we proceed? First of all, notice that in this model that I just showed you, there is no residual error term. Like in the linear model, there is no error term now. That's because of the way that estimation is done in the classical approach to generalized linear models, but it's not really interesting for us where this comes from. What's interesting for us is that once we have estimated the parameters alpha and beta, we can always work out the probabilities for every possible set size that we are interested in, that we had in the experiment, right? And that was this equation that I derived for you a few minutes ago, right, in the previous lecture, right? Okay, so to summarize, the basic model assumes a Bernoulli likelihood generating the 0-1 responses. The model is fit on the log odd scale. So this y is now the log odds here, the eta is the log odds here, and we've got, as before, what has not changed is that we have an intercept and we have a slope. So we are going to be looking at prior distributions for these, and then we're going to have to look at the posteriors and posterior predictive distribution and so on, right? And we can always convert back these eta estimates on the log odds scale. We can convert them back to the probability scale, as I showed you earlier. And of course, I'm going to do that now. Okay. All right, so just as a piece of information for you, there are two useful functions in R. As you know, for every distribution, there's the dpqr family. For the logistic function, there's also this family. So the qlogis function gives you the logit that I showed earlier, and the plogis function gives you the inverse logit, right? Of course, you could write this out yourself, but these are available to you, right? Okay, so let's think about on the log odd scale. We want to think about what a reasonable prior for alpha would be, okay, for the intercept parameter. So let's start with a wild guess, normal with a mean 0 and standard deviation 4. Now, a priori, I wouldn't know what this actually means on the probability scale, right? What is the log odds? I don't use it in day-to-day life, so I can't really say, but I can plot the prior predictive distribution to see what this implies, right? So if I look at the alpha parameter, which was defined in the log odd space, and I convert it back to probability space using the formula I showed you earlier, right? I get back a little bit of a surprise, right? The surprise is that this normal 0-4 prior actually implies that my prior expectation is that the probability parameter, right, is going to be either close to 0 or close to 1 with low likelihood for any of the other values, right? This is not a very sensible looking prior for any application that I can think of, especially not the one that we are discussing right now, right? So we are talking about accuracy as a function of set size, right? And so I would not expect the accuracy to just be either 0 or 1, for example. I would expect it to be in the mid ranges or something, right? So this is not a very great prior for the problem that we are studying. So what could be an alternative prior that we can use? What I'm showing you is how I reason, or how we reason in Bayesian statistics about priors. You always do this by plotting out the implications of your prior in the scale that you're interested in, be it milliseconds or probability scale or whatever, and then try to interpret that in the context of your research problem. Presumably you're an expert in your field, in your domain, and you know what a reasonable range of values are going to be. So you use that information to decide what a reasonable prior is. So let's start again with a different prior. Okay, so let's use a prior that is more constrained, mean zero standard deviation 1.5, and then I'm going to back transform it using that formula that I derived back to probability scale, and this time things look much better. So this looks like a pretty uninformative prior. This alpha normal zero standard deviation 1.5 in log odd scale is a pretty reasonable prior on the probability scale because it allows pretty much all possible values, but importantly, it downweights the extreme values, plus 1 and 0, right? These values are downweighted slightly, right? So perhaps I could downweight them even more because it's highly implausible that I would get accuracies of 0 to 25 or maybe 95 I could still imagine, but beyond that probably not for the large set sizes. So I mean, if I was continuing to work on this problem, probably I would constrain the prior to be even more tighter so that it flattens out much more towards the edges. So this kind of flattening out that one can do with the prior is called regularization, and this is one of the most powerful tools that Bayesian methods provide you. In the prior specification, you can modulate the prior such that you can specify the prior so that the totally implausible values given your domain problem that you're working on are basically ruled out a priori, right? That's a very sensible thing to do, and it has huge implications when you start fitting complicated models with hundreds of parameters where you don't have enough data to get good estimates from the data on for the parameters posteriors, but you do have regularization on the priors so that you can modulate, make sure that the posteriors still look reasonable, right? This process is called regularization, right? So I haven't really regularized this prior yet, but it's still better than this one here, right? This one looks like a pretty crazy prior to use, although you could still use it and nothing bad would happen, so you can try it out and see what happens, right? And the reason nothing bad would happen is that the data will overwhelm the posterior. Because there's so much data, there's going to be very little influence of these kinds of vague priors on the posterior distribution for the parameter. And so, as I said, you can go even further, okay? So now you can start putting in more and more informative priors to see what the implications are. But as I said before, the really interesting thing for us is not the alpha parameter, which is the average accuracy, but rather the slope parameter, which tells us the effect of set size on accuracy, right? So that's where all my attention is focused at the moment. And so what I would do is, when I'm actually working on a problem like this, I would work with increasingly informative priors and investigate their prior predictive consequences in the data. So one way to do this, the code is all in the textbook, so you can look at it later. I don't want to distract you with the details of the code right now, but all I have done is that for the different priors for beta and different set sizes, these I'm plugging into the model, into the prior predictive distribution, to the model that produces the prior predictive distribution. I'm getting back for each of the priors and each of the set sizes, I'm getting a range of predicted accuracies. These are the prior predictive accuracies. That's why they're so spread out, because they're agnostic. Right? Almost all of these except this one here, which is very weird, and this one that is very weird because it's got this high weighting for 0 and 1 values. That's not a great situation to set up for a prior because you're already biasing your prior to go to 0 or 1. Of course, as I said before, in these data, the posterior is going to be dominated by the likelihood. So it won't really matter even if you use these. But the other priors that I've got here, they seem to be more reasonable because they're agnostic, which is good because they let the data tell us a bit more about what it has to tell us. And at the same time, they produce reasonable, flat, uniform distributions, right? Okay. It's So this is just showing the distribution of the data a priori through the prior distributions on beta and so on, right? But we can also look at the predicted differences in accuracy between set sizes. So the difference between 4 and 2, 6 and 4, 8 and 6. So these are possible, stepwise differences that you might want to examine for different prior specifications on the beta parameter, right? So this is extremely useful because now you know under each of these prior specifications what the prior distribution on the differences will look like between these two set sizes, right? These sets of set sizes. This is very useful because now I know as a scientist, if I'm working on recall accuracy for the last 20 years, and that's what usually happens to people, right? They're working on one kind of problem for many years. They have a pretty good idea, or they should have a pretty good idea of what the reasonable range of variation is going to be from one set size to the other. Okay, so this is called a sensitivity analysis. I've shown you many examples of this before, but I just wanted to show you that you can systematically set up your workflow even before you've collected your data. You know what the implications are of each of your priors, and nothing stops you from fitting every single model with all the priors that you have one by one to see what the posterior distributions look like. Okay, so that will tell you something about how much information you're getting from the prior relative to the information you're getting from the data. Okay, so for now, I would say that these priors that I chose for the alpha parameter, that flat prior in the probability scale, and the beta parameter was normal prior with the mean 0 and standard deviation 0.1. So that would be this guy here. This seems like a reasonable prior to choose, so to look at to fit the model, right? I could have chosen a more vague prior, or even these priors, and they would still have been okay, as I mentioned earlier. Okay. All right. So the next thing that we will do is we will fit the model, and then, as usual, examine the posterior distribution of the parameters and try to draw our inferences from it.